Good morning everyone, or good afternoon, good evening, wherever you are or whatever time you're watching this. If you remember in the last video, we talked about trestles, and I said to you that in this section of the course there are generally speaking, four types of questions that you could get in this part of the course. Part of the course that relates to equilibrium. There are trestle questions, signpost questions, ladder questions, and things that hang. Today we're going to deal with signpost questions. And I have not written down the question, but I've got a situation here which is very similar to the sorts of situations that you are going to encounter. And it's a signpost question. So what we've got here is a post, a beam. The beam has, it's a uniform beam. Okay, now what does that mean? Remember, it means that the weight acts through its middle. Okay, so the center of gravity acts through the middle of the beam. So it's not a light beam. Light in physics means that its weight is negligible. Okay, so we've given it a weight. There is a lamp hanging off the. I've called it a signpost question, but I put a lamp at the end of it. But it could be a sign, and the sign could say Canning College. And what we've got here is the beam is being held in place by a cable, and I'm just going to write down here the direction of the tensional force on the cable, and you can see here that it's an upward force. Why is it an upward force? Why is tension acting upwards? Good question, glad you asked. The answer is very simple, because if that cable was to snap, the beam would fall down. Okay, so the cable has to be providing some sort of an upward force, which we call a tensional force. As always, I'm going to label the important parts of this diagram. And remember what I said last time, if you've got a good diagram with lots of information, you don't need a data key. You need a summary of information on the left-hand side. Okay, so I'm going to label this point A, I'm going to label this point B, point C, and point D. All right, and I've got another diagram over here. I'm not sure how well you can see this, but here's another example of a type of question that fits into what I call the signpost category of question, and it's a crane. And you can see the similarities here. You've got the post, you've got the equivalent of a beam, you've got a tensional cable, and you've got the beam has got some weight, and there's something hanging off the end of a beam. And these questions are very similar, with some extra bits that we have to take care of in solving this question. But I'm not going to get to that today. All right? So I'm going to remove this. You've all had a good look at that. Cranes look similar to signposts or lampposts. It could also be some sort of a bridge. There you go. There's a bridge. There's a cable that's pulling the bridge up across the river when you want a ship to go under the bridge. There's not enough space. All right, so I'm going to get rid of this for now. Okay, so I've labeled my critical points, and there are two things that you could be asked in this sort of question. Typically, two things that could be asked. The first is, we want to find the tension in the cable. Okay, so I'm going to write down to find tension. All right, to find tension. That's the first thing that you could be asked in this sort of question. To find the tension. Now, to do this, I'm going to once again go back to my definition of moments. It's the force multiplied by the perpendicular distance from the line of action of the force to the axis of rotation. So I've got a sense that this is going to be my axis of rotation. I'll explain why in a moment. All right, so I'm going to draw the perpendicular force, which is actually going to be the vertical component of tension in the cable. All right, now let's look at, let me get rid of this. Let's transfer part B over here. And I've said this is 60 degrees, so therefore we're going to have 30 degrees over here, 30 degrees, and we've got 1, 2, 3, so 60 degrees over here, which makes these alternate angles. All right, that's 60 degrees, and it means that what I'm going to have here as the vertical component of tension, you can work this out later if you like, but that's going to be T cosine 60. All right, you figure that out on your own. Now, as I said last time, we want to find out what tension is, and it is a moment type question. If I want to use the first law of equilibrium, sum of all forces up equals sum of all forces down, well, problem is there are some forces acting here that I don't know about. We're not clear about what those forces are at the moment. So we've got forces acting here, we've got an unknown over here, and we've got two knowns down there. So there's two variables that we don't know. So we have to go to the second law, which means we're dealing with the sum of the clockwise moments equals the sum of the anti-clockwise moments. But we need a turning point. The turning point can be anywhere, but I'm going to choose the turning point to get rid of one point where there are variables that I don't know anything about. So at this stage, that's going to be point A. All right? Why? Because the post is doing something to the beam. It's supporting the beam in a vertical way and in a horizontal way, and we'll talk about that in a moment. So to find tension, what I'm going to say, take moments about point A. All right, now if we take moments about point A, this becomes our turning point, also known as our fulcrum, also known as our pivot. All right, we take moments about point A, which means the weight of the beam is going to be producing a clockwise moment about point A. The sign or the lamp at the end of the beam is going to be producing a clockwise moment, and both of those are going to be what's the word I'm looking for? Both of those are going to be put into equilibrium by an opposite moment, which is going to be the vertical component of tension in the cable, which is producing an anti-clockwise moment. All right, so I hope that's clear. And I'm just going to acknowledge that T cos 60 is producing the anti-clockwise moment or torque. And so therefore I'm going to keep all of that to the left-hand side of my equality. All right, so sum of the anti-clockwise moments must be equal to the sum of the clockwise moments. And what are the anti-clockwise moments? T cosine 60 multiplied by, what's the distance from the point of application of the force in the cable to the axis of rotation? Well, I've given it to you there. It's 1.3 meters. And that's our only anti-clockwise moment. What are the clockwise moments? The clockwise moments are going to be given by these two forces. All right, so that's 3 times 9.8, which that's the weight of the beam, multiplied by the distance, which is half of 1.8 because it's a uniform beam. So that's going to be 0.9 plus, okay, now I'm going to have to go a little bit down here, the load at the end of the beam, which is going to be equal to 2.25 multiplied by kilograms, multiplied by 9.8 to convert to newtons, multiplied by the total length of the beam, which is 1.8 meters. All right, so therefore we can see that tension is going to be equal to all of this divided by 1.3 cosine 60. All right, I'll let you figure that out, but I have already done that for you. I get 101.76. I think that's what I get. Yes, that's exactly what I get. And expressed to three significant figures, which is what I always like to do, particularly when all of the data is expressed to three significant figures. I tell a lie. That should be 3.00. Pardon me for that. All right, so what I'm going to get here is 1.02 by 10 to the power of 2 newtons. And I'm going to underline that. So once again, let's go back to our fundamentals. I've got a good diagram, which is clearly labeled. I've defined what point I'm taking my moments about. I've stated my equation for the principle of moments. I've filled in my information, and I've underlined my final answer to three significant figures with units. Okay. Now, the second thing that you could be asked in this sort of question is, what is the reaction force, the total reaction force that the post supplies to the beam, or the beam supplies to the post? Well, today I'm going to think about what's the reaction force that the post supplies to the beam. All right, now I think the best way to do. Jonathan, can I borrow you for a moment, please? Now, Jonathan looks exactly like that. Can we see both Jonathan and the diagram? That's great. Okay, now, Jonathan, I'm going to put a load at the end of the beam, like so. So Jonathan can feel this in his chest now, which means in order to maintain this equilibrium, if the beam is pushing into your chest, then his chest must be providing a reaction, a horizontal reaction force in the opposite direction, that way. Okay? And now, Jonathan, you can also feel the beam pushing upwards. Now, if the beam is pushing upwards on Jonathan's chest, it means that Jonathan's chest must be, in order to maintain equilibrium, providing a reaction force downwards. Okay? However, this situation is a bit different to our diagram because I've got a significant load that's actually bigger than the weight at the end of the beam. The beam has a weight that's actually bigger than the load. So I'm going to take this weight over here now. I hope this is okay. And I'm going to put this over here. Now, can you support this, Jonathan? All right. Now, Jonathan, before I put the load on, the end of the beam was pushing upwards. If I put the load on, the beam is now pushing downwards. Downwards, okay, which means Jonathan's chest has to actually, it's going to go, okay. Jonathan's chest has to provide a vertical reaction force that's acting upwards. All right, so let's just summarize that. When there was a load on this part of the beam, Jonathan's chest was providing a reaction force upwards to stop the beam from slipping down, and outwards to stop the beam from pushing through Jonathan and impaling him. All good, thank you, Jonathan.
You're welcome.
So let's solve this question now, okay? Because what we want to do in this part of the question is to recognize that we've got something happening over here. We want to find the the reaction force, R total, of the post on the beam. All right, post on the beam. So what I've got here is just like the case with Jonathan. There's a reaction force acting upwards. I'm going to call that RV. And there's a horizontal reaction force acting outwards, and I'm going to call that RH. And look, guys, you have to make a decision here as to what you want to do with RV. I'm choosing upwards. Okay, in other words, the post is providing an upward vertical force on the end of the beam. If we get the direction wrong, the mathematics will actually work it out for us, and we'll get a negative answer for RV, which means we just reverse the direction of RV. Okay, to find R total, now we can see here that R total is going to be made up of two bits. It's going to be made up of RV and RH added vectorially. And here we're going to have R total, and we're going to need an angle there as well. So R total, that's what we're trying to find. Okay, now let's look at RV for starters. Okay, now we've got, I think we can just use our first rule of equilibrium, first law of equilibrium. We get an upward force, we've got an upward force, we've got a downward force, we've got a downward force, and those are all our up and down. So therefore we can say to find RV, the sum of all forces up must be equal to the sum of all forces down. Okay, I'm standing in front of the board there, not good. Now the forces up are going to be RV plus T cos 60, T cosine 60. Those are our two upward forces. What are our two downward forces? Let's just keep these as variables at the moment. The weight of the beam plus the weight of the lamp. Okay, now let's fill in our information. Okay, we can see straight away that we've got RV is going to be equal to, in fact, let's rearrange first. mg of the beam plus mg of the lamp, subtract T cosine 60. I think I'm going to run out of space here. Okay, so I'm going to start writing a bit smaller. Okay, so let's put some numbers in here. What's the mass of the beam? The mass of the beam is 3 times 9.8 to convert to newtons, plus the mass of the lamp, which is 2.25 times 9.8 to convert to newtons, subtract tension, which we've calculated over here. I'm going to keep it nice and accurate for now, 101.76 cosine 60, And that comes out to, if you work all of that out, I get an answer of, what is my answer? I get an answer of 0.57 newtons. 0.57 newtons. Okay, and I'm not going to underline that because that's not my final answer. That's just the vertical reaction force that the post supplies to the end of the beam. Now I want to find RH. Okay, and I can see very clearly from this, in this situation, I've only got one force acting to the left, which is the horizontal component of the reaction force, the horizontal component of the reaction force that the post supplies to the beam. And that is being, well, the opposite of that is going to be the horizontal component of tension. All right, so the horizontal component of tension. So I can see here, and you can have a close look at this a bit later. Okay, RH is just going to be equal to T cosine 60. All right, so the horizontal component of tension is going to be in that direction, and that's going to be T cosine 30, not 60. Okay, when I put those numbers in place, okay, keeping it nice and accurate, 101.76 multiplied by cos 30, and that gives me 88.1 newtons, which I'm not going to underline because it's not my final answer. So, to find our total, all right, which is represented over here on my two diagrams over there, we can see that using Pythagoras' theorem, R total all squared is going to be equal to RV plus RH added vectorially. So what do we have there? We've got RV is 0.57 squared plus 88.1 squared. So that's RV, that's RH. Have I got that the right way around? Yes, I do. And so therefore our total is going to be equal to the square root of 0.57 squared plus 88.1 squared. And that comes out to be, in fact, 88.1. It's the same as the horizontal component, because look how small the vertical component is in this question relative to the horizontal component. So we're going to get the same number. It's going to be very, very close, 88.1 newtons. And then to find, and I'm not going to underline that, that's not my final answer either. To find theta, I'm going to use tangent, because tan of theta is going to be equal to opposite over adjacent. So that's going to be, tan of theta is going to be equal to 88.1 divided by 0.57. Have I done that right? 88.1. Yep, I have. And therefore theta is going to be equal to inverse tan of 88.1 divided by 0.57, and that's going to equal 89.6 degrees. So therefore, my final answer, R total, is going to be equal to, what's my reaction force? 88.1 newtons, and that's going to be 89.6 degrees to the post. And now I'm going to underline this, because that's my final answer. Thank you.